Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial on preliminary alignment checks and corrective measures will discuss information that will hopefully assist anyone who is responsible for installing or maintaining rotating machinery, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. The major topics in this tutorial will discuss what softfoot is and why it should be corrected, how you should go about finding your softfoot issues, and the 4 steps necessary to correct this often overlooked and misunderstood problem. One of the tricky problems you will frequently encounter when aligning rotating machinery can be traced to what is elegantly called machine case to base plate interface problems. When a piece of rotating machinery is set onto a base or sole plate or frame, one or more than one of the machinery feet are not making good contact at the foot points on the support structure. This can be attributed to warped or bowed frames, warped or bowed machine cases, improper machining of the equipment feet, improper machining of the base plate, or a combination of all of the above. This problem is commonly referred to as soft foot. Soft foot generally describes any condition where poor or no surface contact is being made between the undersides of the machinery feet and where they are supposed to be contacting the base plate or frame. In my experience, at least 3 out of 4 pieces of machinery have a soft foot that is bad enough to warrant correcting. It has nothing to do with what type of machine it is, what size it is, or what purpose the machine serves. This happens on motors, turbines, pumps, compressors, gearboxes, generators, pillow block bearings. Anytime you try to mate one surface to another, there is a possibility that you will not be making good contact. Why bother with this? What's wrong with just tightening down the foot bolts and get on with the alignment? Well, I can think of 5 good reasons. Depending on what sequence the foot bolts are tightened down, the center line of rotation can be shifted into various positions, causing a considerable amount of frustration when trying to align the machinery. Tightening down foot bolts that are not making good contact will cause the machine cases to warp, upsetting critical internal clearances on components such as bearings, shaft seals, mechanical seals, pump wear rings, compressor staging seals, motor armature to stator air gaps, and improper gear mesh. Over time, residual vibration in the machine will begin to loosen the foot bolts, and the shim packs may possibly work out from under the feet with the soft foot condition there. With loose foot bolts comes a possibility that the alignment may shift into undesirable positions. Localized high-stress areas on the machine case may begin to cyclically fatigue, eventually cracking the machine case. With loose feet, vibration in the machine will cause fretting corrosion and repetitive impacting on the machine case and mating frame, damaging the surfaces. Here, for example, is a shim pack that worked loose under the foot of a generator. Here is what some of the shims look like, and here's another photo of some more damaged shims from a different loose shim pack on the same machine at a different foot. When you walk up to a piece of machinery, it is virtually impossible to visually detect a sawfoot condition unless, of course, the shim packs are sitting beside the machine. So the first question you should address is, do I have a sawfoot problem in this machine? And if I do, how do I determine that? There are two typical ways to determine if you have a sawfoot condition. One way is to watch what happens at the feet, and the other way is to watch what happens at the shafts when you loosen one or more than one of the foot bolts. Either of which is only recommended to do when equipment is not running. People have performed what are known as running sawfoot checks. If I remember, I will address this technique in the tutorial on what to do when you are desperate because you decided to skip the suggestions in this tutorial. If you are going to observe what happens at the feet, the ideal way is to get 4 dial indicators and 4 magnetic bases and set them up at each of the 4 corner bolts. Set a magnetic base on the base plate, set the tip of the dial indicator on top of that foot, plunge the stem of the indicator in a little bit. This doesn't count if the indicator is not touching the foot. Then loosen one bolt at a time and observe what happens to the dial indicator. When you loosened the bolt with a wrench, did the bolt feel like it was already loose? If the foot lifted up, which is usually what happens, and you see more than 4 mils of movement, stop. You have a sawfoot condition. Go on to the first step in the correction process. If, however, you saw very little movement or none at all, leave that bolt loose. Leave that indicator there and loosen up another foot bolt and watch what happens at the indicator at that foot. Continue on until all of the foot bolts have been loosened. If you only have 1 mag base and 1 dial indicator, set the indicator up at one of the foot bolts, loosen that bolt, and watch what happens. No movement? Okay so far. Leave that bolt loose and leave that indicator there and loosen up another foot bolt and watch what happens at the indicator at the original foot. Continue on until all of the foot bolts have been loosened. If, after loosening all of the bolts, and the one indicator showed less than 4 mils of lift, then you can probably say that a sawfoot condition does not exist. Rather than set the indicator up at a foot bolt, you could have set the mag base on one shaft and the indicator on the other shaft at the coupling, and observe for any movement when loosening the foot bolts. Remember, you are not trying to correct the sawfoot yet. You're just trying to determine if you have one that needs to be corrected. The first step in the process is to remove all the shims that are currently under the feet and clean all the contact surfaces. It is a good idea to measure the thickness of each shim pack, tape them together, and make a note where the shims went, like the northwest corner foot. See if the shim pack thicknesses at each bolting plane are the same thickness or if they are different. If they are different, was this intentional or did someone introduce a sawfoot condition by mistake? If nobody kept a record of what they did, then you will never really know for sure. Once the shims are extracted, thoroughly clean the underside of the machinery feet and the top of the base plate, removing any dirt, rust, or paint. This is a very simple sounding statement, but it can be very tedious and difficult to do, particularly with machinery that has piping attached to it. One trick I use is to find some sheet metal or bar stock around 1/16 of an inch thick that's about 1.5 inches wide and about 18 inches long. I then get some 80 or 180 grit emery cloth and tear off a piece slightly shorter than twice the length of the bar stock I found. Then I wrap the emery cloth around the bar stock, lift the machine up about 1/4 of an inch or so, and slide the emery cloth under the foot and saw back and forth, lightly sanding both the top of the base plate and the underside of the foot at the same time. I then blow the loose particles out of the way with an air gun or push a rag under the foot to finish cleaning the surface. Once the points of contact have been cleaned, set the machine flat down on the base plate. If there were a considerable amount of shims under the feet, you may want to consider disengaging the coupling. You might also consider placing the machinery so the foot bolts are in the center of the holes in the machinery feet, and then do a quick rough sideways alignment and a rough shaft end to shaft end distance check and adjustment if needed. If the machine is fairly light, like less than 300 pounds or so, I first see if I can rock the machine across either of the two diagonal corner feet, or see if it rocks from side to side or end to end. Sometimes it rocks and sometimes it doesn't. If it does, I see if it seems to mate better in one position or the other. Then I finger tighten down that bolt just to hold the machine in a stable position for the upcoming gap checks. I then get a piece of paper and a pencil and make a sketch of the foot bolt pattern for the drive system that I am working on as if I was looking from above. I use this sheet to record the gaps I am about to measure between the machinery feet and the points of contact on the base plate. I then get a set of feeler gauges, and I usually start with a 2 or 3 mil thick feeler gauge. Our goal is to measure whatever gaps may exist at 4 points around each bolt hole. I start 1 foot at a time and see if I can slide the feeler gauge under the foot, trying to feed it in from both the side of the foot and from the end of the foot. If it doesn't go, then the foot is probably making good contact. If the 2 or 3 mil feeler gauge goes in easily, I try to feed it in as far as a U-shaped shim would go that is appropriate for that size foot. If that feeler gauge goes all the way in with no binding all the way around the bolt hole, I step up to a 5 mil feeler gauge and try it again. If the 5 mil feeler gauge goes real easy with no binding all the way around the bolt hole, I just keep stepping up to thicker feeler gauges until I find one that fits snugly at one of the 4 points around that bolt hole. Bear in mind that when you get to a feeler gauge that fits snugly at one of the 4 points around the foot, it may not fit snugly at every point around the foot. It is important for you to understand that the gap under the foot may not be an even gap. In fact, most of the time, you're going to find a complex wedge-shaped gap. Once you determine what the gaps are at each of the 4 points around your first foot, record those gaps on your sawfoot recording sheet, or sawfoot map as some people call it. Continue on to another foot, repeat the procedure with the feeler gauge checks, and record what you have observed. Remember, you are working on a drive system that has more than one machine in it. As mentioned, sawfoot can occur on any type of a machine. So, if you are working on a motor and a pump, you are going to have to check, measure, and record any gaps you found on all of the pump feet, as well as checking, measuring, and recording any gaps you found on all of the motor feet. Yes, I know this sounds tedious and sounds like it's going to take some time. It is tedious, and it is going to take some time. No one said this was going to be easy. Here's some photos where feeler gauges were used to check for gaps at the machinery feet. It takes a little bit of practice and a lot of patience to get good at this. When you first start correcting these complex sawfoot conditions in front of people who have never been shown this before, you will probably get some strange looks and questions like, what are you doing? We're supposed to be getting this machine aligned. If they've never been shown this before, take the time to explain what you are doing and why you are doing it. Taking some time now to correct your sawfoot problems so that every time you tighten the bolts down, and no matter what sequence you tighten them, the shaft will always maintain a stable and consistent position. If, however, you don't fix this now, when you attempt to correct the misalignment and the shaft aims in different directions depending on the tightening sequence of the foot bolts, you will end up making several unnecessary shim changes and lateral moves before you achieve acceptable alignment tolerances, if you ever do, that is. Don't be fooled by something like this. Notice there is a fairly thick plate under the machinery feet here. There is a possibility that a sawfoot condition exists on both sides of the spacer plate. Actually, there isn't just a possibility, it is a reality in this case. In this instance, you are going to have to correct a sawfoot condition on both sides of the spacer plate. Okay, you've got all the gaps mapped out at all of the machinery feet. If you're as lucky as me, you don't have an even gap at all 4 points around any of the feet. Welcome to the Sawfoot Club. I know this is going to sound a little strange, but you are going to have to build a custom wedge-shaped shim to install under a foot with a wedge-shaped gap, because a U-shaped single thickness shim is not going to correct a wedge-shaped gap. Let's walk through an example so you can see how to determine the required shim thicknesses and shapes you'll need to correct a sawfoot condition on a piece of rotating machinery. In this example, we have measured the 4 gaps around each of the 4 feet holding the machine to the base plate. Notice that there are gaps at all 4 of the feet, which is very common. There should be 3 points of contact somewhere, or the machine is floating in space. Where are they? The lower left foot is making point contact. The lower right foot is making point contact, and the upper right foot is making line contact with the base plate. The upper left foot is not making any contact at all, so we could probably rock this machine across the upper left to lower right corners. Let's start by taking a look at the upper right foot. There is a 10 mil gap on the outer edge and contact on the other side of the bolt hole. If we install a complete U-shaped shim there, would that correct the sawfoot? Not really. When a 10 mil shim is slid under the foot, the left side of the shim will be pinched where the line contact is, but the right side of the shim will still have a 10 mil gap. In other words, nothing gets fixed. We just raised the sawfoot problem up 10 mils. If you carefully examine the gaps around each bolt hole, you will notice that every foot has a complex wedge-shaped gap. Wedge-shaped gaps cannot be corrected with flat pieces of single-thickness shim stock. At this foot, we are going to have to get some tin snips and trim off a 10 mil thick strip shim and install it where the 10 mil gap is on the right edge of the foot. Now, let's take a look at the upper right foot. Notice that it is not making contact anywhere. To build your sawfoot shim, start with the lowest non-zero number. In this case, it is the 5 mil gap. That 5 mil gap clears all 4 points around that hole, so we're going to need a U-shaped 5 mil shim. The second lowest non-zero number is 10. That 10 mil gap is 5 mils more than the lowest non-zero number, and it clears 3 points around the bolt hole, so we need to install an L-shaped 5 mil shim. The third lowest non-zero number is 17 mils, which is along the left side of the foot. There is not 10 mils there from the first two shims, so we need to add a 7 mil strip shim. Frequently, 7 mil thick shims don't come in a standard shim kit, so we can get a 3 mil and a 4 mil strip shim for those points. Okay, we're halfway there. Let's take a look at the lower left foot. Again, start with your lowest non-zero number. In this case, a 7 mil gap exists at the diagonal points at the bolt hole, so we need an L-shaped 7 mil shim, or rather an L-shaped 3 and an L-shaped 4 mil shim. There is the 15 mils gap in the lower left corner of the foot. 15 mils minus the 7 mils that is there from the L-shaped shims leaves 8 mils, right? So we need 8 mils of shims at the corner point. The lower right foot's lowest non-zero number is 5 mils, which clears 3 points around the bolt hole. So we're going to need an L-shaped 5 mil shim. The second lowest non-zero number is 7 mils, so we need a 2 mil strip shim. The 17 mils gap, which now has 7 mils there from the first two shims, needs a 10 mil corner piece. So here is an example of a sawfoot map. This map shows the gaps that were measured at 4 points around each bolt hole and the shim thicknesses and shim shapes that are needed to fill in the gaps. One thing that I try to do when I install the shims under the feet is place the smaller shaped shims in between larger shaped shims. The shims in the upper left corner would have the 5 mil U-shaped shim on the bottom, the 2 and 5 mil strip shims in the middle, and the L-shaped 5 mil shim on top. The shims in the lower right corner would have the 2 corner shims in between the L-shaped shims. The shims at the lower right corner would have the L-shaped shim on the bottom, the corner piece in the middle, and the strip shim on top. To a certain extent, the stacking order is not relevant as long as you stack the shims so that the thicknesses at the 4 corners of the shim stack adds up to the gaps at those points. If you have to build a custom shim wedge with L-shaped or J-shaped shims or shim strips, As much as possible, try to maintain the outline of a complete U-shaped shim when you stack the shim pieces together. Now, later on, you might have to install additional shims under the foot to change the height or pitch of the machine case when you align the machinery. If the softfoot shim packs are neatly fabricated and stacked together in a U shape, you can easily remove the softfoot shim pack, place the additional shims on top or underneath the pack, and reinstall the entire assembly without disorienting the softfoot shim arrangement. After you install the shim correction under a foot, it might be helpful to feel if the softfoot has been eliminated. To do this, initially finger tighten the bolt, put a wrench on the bolt head, and try to tighten it all the way. If the bolt tightens very quickly, for example, you only have to turn the wrench an eighth of a turn or less, the softfoot is probably corrected. If, however, you have to make a half turn or more with the wrench and the foot feels spongy, the softfoot probably still exists and you have to try rechecking the gaps and try another shim pack. Here's a photograph of softfoot shims ready to be installed under a machine. It's not a bad idea to note the thicknesses of the shims with a permanent marker just in case you drop them. It's also very easy to put the right shims under the wrong foot or put the right shims under the right foot oriented the wrong way. Here's some more softfoot shims getting ready for installation. Frequently, I take these photographs so I can input this information on the machinery data cards we discussed in the first tutorial. Here's an example of a shim recording sheet showing the as found, softfoot, and final shims. The light blue shims were found under the machinery before starting the softfoot correction. Notice the shim pack thickness of the as found shims under the coupling end of the motor. One foot had a 71 mil thick shim pack and the other foot had a 33 mil thick shim pack. Notice the shim pack thicknesses of the as found shims under the outboard end of the motor. One foot had a 60 mil thick shim pack and the other foot had a 30 mil thick shim pack. That's very unusual. There should be the same shim thicknesses under both inboard feet and the same shim thicknesses under both outboard feet when doing an alignment correction. When showing this discrepancy to the person who had previously attempted to align the machine, he stated that he suspected that he had a softfoot condition because he added shims, then took some out several times and moved back and forth sideways several times and never achieved satisfactory alignment. He stated that he used the softfoot function in his electro-optical alignment system before taking alignment measurements, but there was no indication of a softfoot problem when he sequentially loosened the foot bolts as instructed by his system. Apparently, near the end of the third day, trying to align the motor to the pump, he said he just started sticking different shims under the feet, hoping he would get it aligned through fortuitous experimentation. After you have installed the softfoot shims under your machinery, tighten all the foot bolts and check for lift as explained previously. For machinery with a really bad softfoot problem, if you can get less than 4 mils of movement at any indicator after loosening all the bolts, that's probably a good place to stop. Trying to get that last 2 to 4 mils of movement corrected is going to be very difficult. If you're getting more than 4 mils of lift, determine which one of the feet seems to move the most when you loosen the bolt. If 3 of the feet are producing little or no movement and the 4th foot is producing a lot of movement, Leave the shims under the 3 feet that had little effect, remove the shims under the foot that produced a large effect, check the gaps under that foot again with feeler gauges, and compare it to the first set of gap measurements you had. If there is a difference in gaps, use the new set of gap measurements to reconstruct the softfoot shims. I'll be the first one to admit that I have more trouble correcting softfoot than I do aligning machinery. The problem is, if you don't get the softfoot corrected, you probably won't get the machines aligned later on. Softfoot problems are far more prevalent than people realize, and the gaps that exist under our machinery feet are complex wedge-shaped gaps that cannot be fixed with flat pieces of shim stock. Softfoot is not discriminatory. It occurs on motors, turbines, pumps, fans, generators, gearboxes, and pillow block bearings. Anytime you attempt to mate one surface to another, there is a possibility of poor contact. It is not easy to fix, but it is very easy to ignore. The symptoms of a softfoot problem are loose foot bolts, loose shim packs, distorted machine cases that affect internal clearances such as armature to stator air gaps, or improper tooth contact in gears, or rubbing seals in turbines, or uneven wear ring clearances in pumps, and having to make several vertical and lateral moves when trying to correct a misalignment condition. There are 4 steps you should perform to correct a softfoot condition. First, remove any existing shims and clean the undersides of the machinery feet and points of contact on the base plate. Second, set the machinery onto the base and measure at least 4 points around each bolt using feeler gauges. From your softfoot map, fabricate and install the softfoot shims needed to fill in the gap between every foot point on every machine in the drive system. Once the softfoot shims have been installed, verify that the problem has been eliminated by doing lift checks with dial indicators or with an alignment measurement system set up across the coupling.